In Chapter 7, we're going to work on developing a deeper understanding for the information that is available to us on the periodic table. We will begin with a brief history of the periodic table, and then we're going to study nuclear charge. So nuclear charge would be the positive charges from protons within the nucleus. We're going to look at how those affect the properties of atoms. Then there's some trends that we can look at on the periodic table. We'll look at how the size of atoms change as you go across the periodic table. We'll look at how ionization energy and electronegativity change. Then we're going to talk about some of the different groups on the periodic table and how there are some trends that fall within those groups. Let's start with the history of the periodic table. In ancient times, you only had about 9 elements, and they were your metals that were naturally found in nature, like iron and gold and silver. In the Middle Ages, there was a gap where not many elements were discovered, but it really started to pick up in the 1700s, and you see a lot more in the 1800s. So by that point, scientists were looking for a way to organize the elements. 2 scientists in particular are given credit for the periodic table: Dmitri Mendeleev and Lothar Meyer. These 2 were working totally independent of one another, but they came to many of the same conclusions. Keep in mind, at this point, they were unaware of the number of protons in an atom, which is how we currently arrange the periodic table. So they arranged their periodic table by atomic weight. They also noticed that when you did this, there were periodic times where the similar properties would line up with one another. For many of the elements, every 8 elements, you would have similar properties. This was the framework of our current periodic table. In many ways, their periodic table looks very much like ours, because for most elements, if you go in order of atomic weight, you have the same order that we have by going by atomic number. There are a few exceptions to that, but for the most part, their periodic table was in the same order as ours. Mendeleev gets the most credit for the periodic table. Even though he and Meyer had very similar work, Mendeleev did some things that really gave a lot of credibility to his periodic table. For example, in 1871, Mendeleev left a blank in his periodic table for the element germanium. He noted that this element had not been discovered yet, but he predicted that it would have these properties. Later, the element in 1886 was discovered, and here are the actual properties. And if you look through this list, many of these things line up very closely. The atomic weight's close, the density's close. As you go down the list, his predictions, based on his periodic table, are very close to the actual properties of that element. This gave an incredible amount of credibility to Mendeleev. As I mentioned before, Mendeleev's table was based on atomic mass because that's what they knew the most about at the time. About 35 years later, Ernest Rutherford discovered the nucleus. That changed our thought quite a bit about the atom. So Henry Moseley came along, and he's the one who is given credit for our current periodic table. He's the one that said we should arrange this by atomic number, by the number of protons. In this video, we're going to look at effective nuclear charge. Periodicity is the term that refers to the fact that there is a repetitive nature in the properties of the elements on the periodic table. So when you line them up according to atomic number, what we see over and over again is that the elements in the same vertical column, which we call a group, have similar properties. We're going to look at several of these properties, including sizes, something called ionization energy, electron affinity. But first, we need to talk about nuclear charge, because this is what causes a lot of these properties. We learned way back in Chapter 2 about Coulomb's law. This said that the force between 2 charged particles depends on the amount of charge and the distance between them. That comes into play very much when we start talking about nuclear charge. Nuclear meaning the nucleus, and the charge refers to the protons within the nucleus. Here you have a diagram for sodium. Sodium has 11 protons, which means it also, for a neutral atom, has 11 electrons. 10 of these electrons are in inside energy levels, and 1 electron is in the outside energy level. We call that a valence electron. Sodium's valence electron is feeling several different things at once. It's being pulled to the nucleus because it's attracted to that positive charge given off by the protons, but it has all these other electrons between it and the nucleus. So those electrons are going to be pushing it away. So electrons are both attracted to the nucleus and repelled by other electrons. The effect that these inside electrons have on this outside electron is referred to as shielding. These electrons are shielding that electron from feeling the full nuclear force. So this electron's only going to feel part of what it would normally feel from the nucleus because these other electrons are pushing it away. If you take both of those factors into account, we call it the effective nuclear charge. So the actual nuclear charge is what this electron would feel if it were the only electron there. The effective nuclear charge, you take what it would normally feel, but you subtract out what it feels from these other electrons, and that is called the effective nuclear charge. And the effective nuclear charge will always be smaller than the actual nuclear charge. Here is the formula for effective nuclear charge. We use the symbol ZEFF, so that's Z effective. You calculate that by saying Z minus S, where Z is the atomic number, and S is a screening constant. The value for S is usually close to the number of inside electrons. Effective nuclear charge changes in a predictable manner as you go across the periodic table. It increases as you go from left to right, and it decreases as you go down the periodic table. This graph combines a lot of different information about effective nuclear charge. This first line that you see here, the red line, that's showing you what the inside, the core electrons are feeling. Those are in the 1s sublevel, so they are as close to the nucleus as you can possibly get. This is like your control group. They're not being pushed away by any other electrons. And you can see that that's very linear. As you go across the periodic table, this is increasing at a steady rate. These other lines are showing you different methods for calculating Z effective for valence electrons. So these lines are what the electrons in the outside energy level are feeling. Two of these are kind of complicated methods. One is where you just take the number of protons and you subtract the number of core electrons. And you can see that it increases steadily as you go across a group. So all the way from lithium to neon, there's a pretty steady increase. And then right here it drops off because you've gone down a group. So this is increasing as you go left to right. When you go down a group, it's going to drop off and then start to increase again. If we were to really oversimplify the Z effective trend on the periodic table, you would say that it's the highest in the top right of the periodic table.